Welcome today for this seminar. It will be about detect and defense against adversarial examples using natural sense statistics and adaptive denoising. So this work has been done with Hamidouche Anwar, who has interned at INSA. He is now a PhD student at Poitiers, Sid Ahmed Fezza, and Olivier Deforge. So I first start by giving the context and motivation of this work. So in this figure, I give the top one accuracy of image classification models using deep learning. We can see like today, we can reach a very high accuracy of around 90% of top one accuracy for ImageNet dataset, which contains 1,000 classes. And we can see like during the last decade, we have a very high, huge increase in performance from 50 to 90% of accuracy. Now, if we look to the top 5 accuracy, we can see that we can reach up to 98.8% of top 5 accuracy, which is very high, and which is even higher than what human can do today. And we can see also that we have a high progress during the last decade. This progress in deep learning, especially for computer vision application and image classification, has motivated the use of these models in many applications of prominent importance. As we can see here, we can use deep learning and for computer vision application for autonomous driving, security for identification of cars and people, and we can also use it in medical health to detect diseases, for example. So this is the good part of deep learning. Now we can see some limitation of deep learning models. So this first limitation, it was explained very well in this paper of Alexandre Damour, published in 2020. Like he was emphasizing that machine learning models in general are usually optimized on independent and identically distributed data. And when they are deployed in a real environment, they exhibit an inspectively very poor behavior. And this is because they are optimized on this IDD distribution, and when they are deployed, they give a very poor performance, especially on unseen data or on data which are not follow these distributions. So this is the first drawback of today of behind the limitation of deployment of deep learning models, especially in general learning-based models. So the second limitation, which is the interest of this topic today, it is about adversarial attack. Here I give an example about this image with a stop sign. It is organized by a deep neural model, like deep neural model here, as a stop sign at 99%. But if the attacker here added a very small perturbation to this image, it will fool the deep learning model. It will be recognized here as a sign of 120 kilometers per hour speed, which may be very dangerous, for example, in autonomous driving. And so this is what is adversarial example. And we can very easily add some perturbation and fool the deep neural networks. And this can lead to a very dramatic consequences. Here I give example of this video. We have here a Tesla car with autonomous driving. At the beginning, it drives very well, but at the end, it doesn't detect the car behind. It doesn't detect the car up front, and it leads to a crash. And this is mainly related maybe in the condition of the driving in the night, during the night, with different illumination conditions than the data on which it was trained on. But it can also be a consequence of adversarial example if an attacker try to attack this detection algorithm used in the Tesla car. So this is the context, and we can go now to the objective of this work. So this limitation motivate us, but many researchers, we can find in the literature more than maybe 20,000 papers around attacks and detection to develop a defense technique that enhances the performance of the deep neural networks in adversarial example-prone context. And the idea is also to preserve the good performance of this deep learning model on clean images, which are not attacked. So this is our objective: enhance the deep learning model performance in when the image is attacked, but also keep the good performance of the models on clean images, exactly like what I showed at the beginning of this presentation. So this is the context of the motivation of this work. So please feel free if you have any question to ask. Now I will go to the second chapter, which is the background. This wasn't in the original version of this presentation. I added it to just give some formal definition on what it is adversarial example and how we can generate attacks in deep neural networks. So first, what is adversarial example? So let's X is a clean example in space X, and Y it's label. So here we can find Y, which is equal to f theta x, and f theta x is the parametric function of the deep neural network. So we give to the deep neural network an image X, and it's give us a label Y. So this is X is clean image, and Y is the right class. Now, what is adversarial example? It's X prime, which is also in the same space X, such as f theta x will be different from f theta x prime. So the label of the original image and the label of the adversarial example will be different. And the second condition also is that the clean image and the adversarial example will be close in terms of distance, in terms of distance, and it will be bounded by this epsilon, small epsilon constant. As we can see here in this figure, if we have a clean image X here organized as a cat, the adversarial example is all images, all like images which are outside the boundaries of the cat class, but with a minimum distance with the clean image X here. So the distance between X and X prime, it will be bounded by this epsilon constant. So this is the formal definition on what it is adversarial example. And we can have untargeted adversarial example, which means that we change the label to any other class. And we can have a target adversarial example, which means that we change the label to a specific label. For example, if you want to organize a cat as a dog, so this is a target adversarial example. And untarget, it's like we just want to change our initial class without any specific target class. Usually we work more on untarget adversarial examples. So now in the literature, there are many attacks. Here I just try to give a classification, and I will present very briefly some of them. So we can have two categories, white box and black box attacks. What is the difference between white box and black box? White box, when the attacker generates the attack, he have all information about the model and the parameter of the models that help him to generate the attack. And in this category, we can find gradient-based optimization, like they usually rely on the gradient, or other attacks that try to solve some constrained optimization. So now, black box attacks. The black box attacks doesn't have access to the model parameters. and the model layers. So the black box attacks, it will generate the attack only knowing the input, so the image, and also the label, its label of the after the model. After processing the image by the model. So the black box attacks doesn't have information on the layers, the parameters of the model. So it tried to generate the attack with using some gradient approximation because it doesn't have information to how derive the gradient in back propagation. Some others try to use the decision, approximate the decision boundary of the model. Other models try to search around the clean image to find an image which is an adversarial example. And as this research, some use some evolutionary algorithms. So this is I give general idea about how to generate adversarial attack. Usually what we have to keep here is what is white box attack and what is black box attack. So in white box attacks, we can have a very good attacks because we know the parameters of the model. In black box attack, it's more difficult because we don't know the parameters of the model, but we can estimate them with different solutions. So we can see now how to generate attack. We will focus on this gradient-based optimization, which is the main used attack in the literature. So we see here how to generate the attack. So the idea is we have clean image recognized as the bus. We added here some perturbation, which is the sign of the derivative of the loss function, weighted by this epsilon small constant. And we added this to the input image, and we find the attack. As you can see here, this fast gradient sign method, it's very simple. It just added the sign of the derivative of the loss function, bounded by this epsilon constant. It's one-shot gradient-based attack. It's performed in one step. So it is very simple. But the main issue maybe of this attack, that's when we generate the attack, we don't know if it works or not. We don't know if the output is adversarial example or it is in the same manifold of the original image. And as you can see here, we have the bus, color bus. We added a small perturbation, and we don't even can recognize that there is perturbation in this output image, and it is organized as ostrich. So this is a very simple first attack called FGSM, and then they proposed several other attacks based on this idea. So the second idea, it is the basic iterative method attack, which is exactly the same than FGSM, but it is iterative. So we perform the attack in different steps, and at each steps, it is iterative. So the attacked image, we added another perturbation, which is also the sign of the derivative of the loss function. And each time we test if it is adversarial example or not. Up, we reach a maximum of iteration we want to have. Especially higher is the number of iteration, more efficient is the attack. And as you can see here, the initial value of the x0 prime of the first attacked image is the clean image. And one of improvements proposed later, it is the projected gradient descent attack. It's exactly as the beam attack, it's iterative attack. The only difference we can see is that the initial value of the first attacked image, x0 prime, it is not the clean image, but it is like a perturbed image, which is randomly perturbed, but bounded in this area, bounded by this small epsilon value. So the objective of this chapter of adversarial attack, it was to say like we can perform different types of attack, and we can categorize them into white box attacks or black box attacks. And then we showed here how we can generate attacks with using gradient descent approach. And we have seen 3 different types of attacks like FGSM, beam, and PGD. So beam, it's one-shot attack, and FGSM and PGD BIM and PGD, sorry, are iterative attacks, but the three are based on the sign of the gradient of the loss function. So feel free if you have any question or. So now we can move to the third chapter, which is related work. So since here we propose a defense technique, so I give some information also on defense techniques. So in defense techniques, also as attacks, there are many defense techniques. Maybe in the last 5 years, we have more than 10,000 papers for defense. It's difficult to present all, but here I give 2 categories. So we have defense techniques that based on detection. So what does it mean detection? Detection, it means when you receive the adversarial example, you will just say if it is adversarial example or not. So you don't try to project back the image to its original class. So detection, it just say, okay, I received an image. I will be able to say if it is adversarial example or not. And in this detection class, we can have several categories also. For example, we can have feature squeezing. Feature squeezing is we will process the adversarial example, like the input image, we will process them with different operation, and we compare the output of this different operation if you see if they are different or not, and this helps to detect if it is adversarial example or not. One category is statistical analysis. For example, you apply a principal component analysis of the image, and then you will try to find if it is attacked or not. Some attacks based on adversary detector networks. It's a network that is able to detect if the image is adversarial or not. It is trained to detect. And other what we call auxiliary models or network invariant, we can add some features inside the model of the classification to also give us the output, so the label, even if it is adversarial label, but it's also able to say if this image is adversarial or not. So we have 2 outputs. One is for the label as ImageNet, as like VGG16, for example. But it gives us a second output, which is to say if it is adversarial or not, based on the intermediate layers of the VGG16 model. So on the other hand, we have what we call defense technique. Defense technique, it will try to project back the adversarial example to its original manifold. So it's different from detection. It doesn't only detect, but it also try to project it back to its original manifold. So in here also we can find several categories. We can have adversarial training. So adversarial training is just to add adversarial example into the training of the model. For example, you train VVG16 with adding adversarial example to the training set. And we will have VGG16, which is more robust to adversarial example, but this solution doesn't generalize well to unseen attacks, for example, because every day we have new attacks. So we don't know if the not included attacks will, the model will be robust or not to these new attacks. We have also the distillation method. Distillation, it's like to train another network, which is robust also to this adversarial attack. Feature denoising block, it's using some denoising blocks inside the models. For example, inside the VGG16 at each layer, we added some denoising blocks because it has been shown that this perturbation propagates also among the layers. So this denoising blocks with the trained parameter, they will be trained to remove this adversarial perturbation and of course propagate back the image to its original manifold. And also the last approach is the pre-processing approach. So this is the main focus of this work because our proposed model is also based on pre-processing, and the pre-processing try to pre-process the input image before giving it to the model. And we will see what are the objectives of this pre-processing models. So the first objective, of course, is to project back the adversarial example to its original manifold with using filtering. For example, you can perform filtering to remove this perturbation. We can use some here we can use some generative adversarial network that project back the adversarial example to its original distribution. So it's based mainly on the distribution to project back the distribution of the adversarial example to the clean distribution. And the second objective of this pre-processing methods is also to introduce some masking and gradient masking and obscuring, which is a very powerful technique because it will prevent to generate the attack on this model. Because as I explained before, when you have adversarial example, we need this gradient information to generate the attack. But if we added some non-linear, non-differentiable process, or if we added the randomness, it will be difficult to estimate the gradient of the model with the attack. So it will be difficult to generate the attack on the model. So this is the two objectives of the defense: project back the adversarial example to its original manifold, and also introduce some gradient masking to make it more difficult to the attacker to generate the attack, because it is based on the gradient estimation. So here I give two examples. So we have here two defense techniques based on pre-processing. The first one is the thermometer encoding. So this thermometer encoding, it's process the input sample with an extremely nonlinear function that includes especially quantization and discretization. So these two steps, they are extremely nonlinear. So it makes it difficult for the attacker to generate the attack when we added this thermometer pre-processing step. There is also the MNIST, which also tried to add some randomness with randomly dropping some pixel in the image, and then it used matrix estimation to estimate this dropped pixels. So what the MNIST try to do is to add some randomness and also remove some pixels, but randomly, and this will alterate the perturbation and also make it difficult to generate attacks on this pre-processing, because random process, it's also difficult to, it's non-linear, it's non-differentiable, so it's difficult to generate attack based on gradient descent attacks. But however, there are two main limitations of this solution, because there are some solution which is called expectation oval transformation that and also backward pass differentiable approximation that that's allow to approximate this nonlinear function and also this randomness. So if we are able to approximate this nonlinear function and randomness with linear estimations, so we can still perform attacks with using this gradient-based attacks. And the other problem also we try to avoid in our solution is to, when we perform this pre-processing, if we perform this pre-processing on clean images, the problem is that this pre-processing will decrease the performance of the deep neural network on clean images. So because when we perform the pre-processing in this solution, we perform it on all the received image. So if we receive adversarial example, it's okay. But if we receive a clean image and we perform this pre-processing, since this pre-processing will decrease the quality of the image. So of course, we will also decrease the performance on the classification of the model on this clean processed images. So this is the objective of this chapter, like to see for the defense technique, we have two categories. The first category is to be able to detect adversarial example, and the second category is the defense, is to be able to project back the adversarial example to its original class or original manifold. And we have seen the two main limitation is if we add non-differentiable function of randomness, we can still estimate this with a linear function. And also the mainly limitation is that if we perform the pre-processing on all images, it may decrease the performance on the model on clean images. So now we can move to the fourth chapter of the proposed model. So here I give the main idea of the proposed solution, and it is based and try to explore here the concept of divide to conquer, because defense, it's a very difficult task. So we try to separate it in two main tasks. So as you can see here in this model, we have the input image, which is first processed by a detector to detect if the image is clean or adversarial example. So if it is clean here, if the detector detects that the image is clean, it will directly feed the classifier, okay? But if it is detected as adversarial example, it will be processed here by a denoising block, which is based on a block matching 3D filter and some optimal estimation of the denoising parameter. Because why we need this adaptive denoising? Because we can have different types of attacks, and also we can have different levels of perturbation. So we have to provide a denoising which is adaptive to different attacks and also adaptive to different level of perturbation. So this is the idea. First, perform the detection and then perform the denoising only if the image is detected as adversarial example. And this will, if we have a good detector, this will prevent to decrease the performance of the model or denoise the image if it is clean. So if it is clean, we will keep the same performance of the model without this defense technique. So now I will explain how we perform this detection and the denoising. So first I start with the detector. So the detector is based on the concept of natural sense statistics. It is used a lot in image quality evaluation. And the first idea is to compute the mean subtracted construct normalized coefficient. So here I is the input image. Small ig are the two components of the pixel. And here what we do with this operation is just subtract a local mean around the pixel, and we divide it by a local standard deviation. Like it is such a normalization of the image. And why this is very important for detection of adversarial example, we can see it in this example. So here, the first row, it gives us, the first one is the clean image, and then we have three images attacked with three different attacks, so FGSM, PGD, and CW. And here in the second row, we can see the MSAN coefficients. As we can see here, when we added the attack, we alterate this MSN coefficients, because here for natural images, MSN coefficients here, we can see that we still have some details about this, butterfly that we don't have anymore when we added the perturbation. And what is the main idea behind this is, as we can see here, the distribution of this MSN coefficient of these four images. We can see like the first image, which is clean, the MSN coefficient distribution, which is represented here in green color, it's like a Gaussian distribution. But when we added some perturbation with three different attacks, we see like the distribution of the MSN coefficients doesn't anymore follow this Gaussian distribution. And the idea is to be able here to use this property of Gaussian distribution to detect if the image is adversarial example or not through the MSAN coefficients. So for this reason, for the first step, we perform the computing of the MSN coefficients. And now we will see the second step, how to try to estimate this distribution from the MSN coefficient of the image. So now we will compute some parameters that will be used as features. So the first parameters we consider like modeling this MSN coefficients with a generalized Gaussian distribution. So for this generalized Gaussian distribution, we need two parameters, which are the variance of this GGD, which is sigma squared, and also the shape of this GGD distribution, so which is beta here. So for each image of MSCN coefficients, we will estimate two parameters, which are beta, the shape of the GGD distribution, and the sigma square, which is the variance of this GGD distribution. So now you can count with me. We have two features, okay? Because at the end, we will end with 18 features. And now we also added some other distribution to have a better estimation of this distribution. And here we use also the asymmetric generalized Gaussian distribution. This is a distribution which is asymmetric, and we have here I give the distribution. We have like two parts, the left part and which is centered here, and we have the left part and the right part of the distribution. And here we have the parameter, the variance of the right and the variance of the left part. And we have also other parameters which are new, which is here, and eta, which give us like information about such as the mean. So here, for the asymmetric generalized Gaussian distribution, we have four parameters that we can estimate. So here we have new two variances of the left and the right part of the distribution, and we have also this this eta parameters. So here we have four features, but here we don't estimate these four features for the MSN coefficients itself, but we estimate it for four other variables, which are horizontal information, vertical, first diagonal, and second diagonal, which are computed from the MSCN coefficients. So to summarize, we have two features from the GGD distribution. We computed here, beta and sigma square. And for each orientation, like horizontal, vertical, first diagonal and second diagonal of the MSN coefficients, we will have four parameters of the AGGD distribution. So in total, we will have 16 features of AGGD distribution and two features from the GGD. So in total, we will have 18 features from MSN coefficients of an input image A. So these all 18 features, they will put, we put them in a vector of features, F, we call here F. And these features will feed a binary classification, which is SVM model with a sigmoid kernel that will detect if input image, if it is adversarial or not. So if we have 1, the image is detected as adversarial. If we have 0, the image is detected as clean. And here, since these features, we see like there are too sensitive to distortion that are added by the attacks, we think that it will be efficient to detect adversarial examples. So here to summarize this model, so we have input image here I, we compute MSCN coefficients, then we estimate the coefficient of two distribution, generalized Gaussian distribution and the asymmetric generalized Gaussian distribution. We end with 18 features that feed the SVM classifier to classify if the image is clean or not. So this is the first step, which is the classifier. Now I move to the second step, which is the denoising. And the denoising is performed only when the image is detected as adversarial example by the first block, which is the detector. So the denoising, we use also adaptive denoising, as I said before, because we can have different types of attack and we can have also different level of perturbations depending on the attacked image. So we need also adaptive denoising in terms of denoising. So adapt the threshold of denoising, but also the perturbation can be distributed differently in the image depending on the local variation of the pixels. So the adaptive denoising with using block matching 3D filtering, it's very well for this to answer to this problem. And so it is performed in 3 steps. So the first step is to which is classification, is to build a pile of patches with the same characteristic, spatial characteristic. So the idea here, as you can see in this image, we have a P patch here, and we try to find inside these windows all the parameter, all the patches Q that have the same characteristic of this P patch, and how to know if they have the same characteristic or not. We just use a distance between these 2 patches, P and Q, and if this distance is lower than a threshold, we will say like these patches are the Q patch is similar to the P patch, so we will put them in the same pile. So the idea here, this classification step, we will have different pile of patches, and each pile of patches which will have the same spatial characteristics. Okay, this is the first step. And the second step, as we can see here, we perform a 3D linear transform, which can be, for example, a 3D DCT transform. And then we perform some denoising with using shrinkage operation. As we can see here, we have this pile of patches, and then we perform this to3D, which is a 3D linear transform, and then we perform a thresholding operation, which is given here, which is hard thresholding operation, and then we perform inverse 3D transform. So forward 3D transform, thresholding, and then inverse 3D transform. So the thresholding is very simple. It just put the transform coefficient to 0 if the coefficient in absolute value is lower than a threshold, and also otherwise we keep the coefficient as it is if the coefficient is higher than this threshold. So as I said, this threshold is very important because it will give us the level of the thresholding we will perform. And the third step of this 3D block matching filter, it will exactly be the same than the second step, but here we perform not a 3D linear transform, but we perform a winner transform filtering. But this winner filtering transform, it is performed on already filtered piles of patches already filtered by the second step. So to summarize this step, so we perform a 3D block matching denoising following 3 steps. So the first step is to put all the patches with the same characteristic in the same pile. Then we perform the denoising of each pile separately with using a 3D linear transform, for example, DCT, followed by thresholding, and then perform exactly the same operation with using a winner filter instead of a 3D linear transform. So the last operation, as I said before, we need adaptive denoising. So this lambda 3D parameter, which is used here to denoise, which is used here for the hard denoising, it will be estimated from the input image. So when we have input image, we proposed here different architectures of convolutional neural networks that estimates these parameters to perform the optimal denoising to project back the image to this original manifold. And here, for example, I show example of a convolutional neural network which was used to estimate the optimal denoising parameters for a color image. So as input, we will have our image, and output, we will have 3 lambda 3D. Each one will be applied to a color component, especially here for ImageNet dataset on RGB components. So this is the solution. It is so based on detector with relying on the MSN coefficients and GGD and IGGD distribution. And then if the image is detected as adversarial example, we will perform denoising with using 3D block matching denoising with adaptive parameters. Now we see how we evaluate the performance of the proposed model. So as experimental setup, we use 3 datasets, which is which is mostly used in the literature, which as MNIST, CIFAR-10 and Tiny-ImageNet. Here I give the classification accuracy of this model, which were used without on clean images. So in terms of attacks, we also consider 3 attacks: FPGD, FGSM, PGD, and CW, under black box, gray box, and white box settings. And we also compare the solution with 3 defense techniques, which are MADRI, I didn't present, but the thermometer, and MNIST, I have presented this in the related work. So first, we try to evaluate the performance of the detector itself. So how we can evaluate the performance of the detector? What we need? Of course, detection accuracy, but also we need to have a very low false positive. Because it's important to detect clean images as clean. So we need a very high accuracy, so detect adversarial example as adversarial example, but we also need to detect clean images as clean, and this is evaluated with a false positive rate. And in this table, I give here the accuracy for the 3 datasets, MNIST, CIFAR-10, and Tiny-ImageNet, and 3 attacks, FGSM, PGD, and CW. And here we give the false positive rate. As we can see here, the detector is very efficient, and it reached perfect detection of 100% detection on all datasets and against the 3 attacks. Except for Tiny-ImageNet, which is more challenging, we perform 98% of detection. And what it is important also is to have a very low false positive rate, which is here lower than 2.3 for the ImageNet dataset. This is very important because if we have very low false positive, we keep the performance of the deep neural network on clean images because we don't process clean images with the denoising process. And here we show in this figure the receiver operating characteristic curves on CW attack under white box settings. Here in 3 different colors for the 3 different datasets, MNIST, CIFAR-10, and ImageNet. As we can see here, we have a perfect detector with an area under curve, which is estimated to 99%. Sorry. So now we showed the performance of only the detector. As we can see with this detection solution, we can perform a very high detection accuracy with a very low false positive. Now we will see the performance of the denoising. Here we show the performance of the denoising of the defense on the example that are detected as adversarial example, of course. And here we give the performance for three attacks: FGSM, PGD, and CW. As I said before, PGD is iterative attack, so we can perform the attack at different steps. Here we perform 4 different steps. Of course, higher the number of steps, more efficient is the attack. And here we compare our solution to 3 state-of-the-art solution defense techniques on 3 datasets: MNIST, CIFAR, and Tiny-ImageNet. And in this colors, I give in green color the numbers where our solution is ranked the first, and I give in red color the performance when our solution is not the first. So as we can see, for the most of the configuration, our solution is performing the highest accuracy for attacked image. So it's back propagate to the original manifold the input image that detected as adversarial examples. This is very important, and for MNIST, for example, we can reach a very high accuracy, higher than 97% in general. However, when we are when we work with CIFAR-10, it is more challenging, but we still perform the highest accuracy. And on Tiny-ImageNet, we also perform high accuracy, around 67% of accuracy. And this performance is given in black box attack settings. So black box attack settings is not the most efficient attack. So we will see our performance in gray box attacks, as we can see also for 3 different attacks and also 3 different datasets. Our solution performs almost the best performance, with all the accuracy are given here in percentage with a green color. For some configuration, we don't perform the highest accuracy, but we are not far from the best performing approach, with less than 1% difference in terms of accuracy. Here we can see we have 2%, but the difference is very low. Now here we evaluate the performance of the proposed attack on the white box attack setting, which is the most difficult to defend against, because the attacker has the parameter of the models to generate the attack. As we can see here, even in white box settings, we can reach a high accuracy, especially on MNIST. We have the highest performance. And here we, for different steps of the PGD attack, of course, we have the highest accuracy. For some configuration, we are not far from the first, with around 1% or 2% difference. But for higher attack steps, we have always the highest accuracy in this challenging against these challenging attacks in white box settings. So here we see some visual illustration of our defense technique. So here we have the clean images in the first row. In the second row, we have the attacked images, for which we added attacks, and they are adversarial example. And in the third row here, we have the denoised examples, the denoised images. We can see like the denoising can generate for some images some blurriness, but the quality still remains good. And this is also explained why we get a high accuracy even after a denoising process. And this is also mainly related to performing adaptive denoising. So this is the end of my presentation. So to conclude, so we proposed a 2-stage defense approach, which is based on NSS MSCN coefficients and 3D block matching denoising. So we divide the problem of defense, which is difficult, into 2 problems, so detection and then denoising, with this divide and conquer. And then we can see like we enhance the DNN classification on adversarial examples. And also we preserve the performance of the classifier on the clean images, because we have a very efficient detector. And we reached also a state-of-the-art performance under black, gray, and white box attacks on the same category of the work, which is based on pre-processing of the input image. So I give in these slides of all the references our work is based on. I give also all the links in the PDF you can access on to all these references. And yeah, thank you for your attention, and please feel free if you have any questions.